we get a step forward towards normal forms or different kind of normal forms, then we know that we need to be sure that and 1NF, 2NF to be sure, BCNF and 4NF to show that we are strong. We need to be ready to normalize a given table. For example, we have first normal form, all values are atomic, no repeating groups, lists a cell. We have multi-valued cell. Then we have 2NF, we have 1NF, no partial dependency. Non-key attributes depend on whole composite key, so non-key attributes depend on the key. We are fixing partial dependencies. Here we don't need to give multiple entries as an array in an entry. In 2NF we make sure that all of the attributes, non-key attributes, are depending on the key of that table. In 3NF we have 2NF plus no transitive dependency. Non-key attribute depends on another non-key, so non-key depends on another non-key. This is not possible. So we need to fix transitive dependency here, meaning that 2NF plus no transitive dependency, like non-key attributes depend on another non-key attribute. We have something that is not a key attribute and they depend on another non-key attribute. This is not possible in 3NF. So non-key attribute must depend on the primary key that we have in the table. Here we have partial dependency, meaning that non-key attributes depend on the whole composite key. BCNF means for every functional dependency x goes to y, x must be a super key, and it's stricter than 3NF. We have we fix odd overlapping keys. This is BCNF. So a functional dependency x goes to y where x must be a super key. BCNF is the fourth normal form is BCNF plus no non-trivial multi-value dependency. We have independent multi-values, so there is no value that is multi-dependent. So my schema form by form is in the report analysis. We have first normal form, every column is atomic. The multi-valued book author and book genre are pushed into bridge tables instead of comma list, like saying okay, author comma, like one author comma second author here, and like things like this. We didn't do it like this. We didn't put multiple values like an array. We put single valued in a single cell. Then that's 1NF. 2NF is single column primary key tables pass automatically, no part of key to depend on. For composite key tables, we have copy borrows table where each non-key attribute depends on the whole key. So we have non-key attributes depending entirely on the key. Copy dot addition depends on book ID and copy ID, not book ID alone. So 2NF is like it's like for it depends on a composite key. So if we join tables that have many to many relation, then we know that these for example another attribute depend on the composite key, not just on book alone. Then we have 3NF, one deliberate exception. So fine amount is deliberate from due date in our case plus return date, a non-key attribute linking to a non-key link. Kept it on purpose because that is the reference we will give. So we're not in 3NF and we normalize it. So we have crisp classic loan where loan ID, student ID, student email. Here loan ID goes to student ID and student ID goes to student email. So student email is transitively dependent. What we do is that we split into loan by saying loan ID comma student ID, and student does student ID and student email. Then we draw the two clean tables and we make split into loan, and we have loan ID and student ID, and we have student with student email student ID and student email. So we have two clean tables. Here we had transitively dependency, for example, loan ID and student ID and student email. Here loan ID goes to student ID and student ID goes to email, so student email is transitively dependent. Student email is dependent. Here it makes no sense, right? We have two keys here. Now we split into loan by saying loan ID and student ID, and here we split into student with student ID and student email. So student only contains information about student itself, nothing about the loan. Loan is something different. Then we have what's the difference between 3NF and BCNF. So 3NF allows an financial dependency where X goes to Y, where Y is a prime attribute part of some candidate key. Even if X isn't a super key, BCNF forbids that. So every determinant must be a super key. So BCNF is a subset of 3NF, where the gap only shows up with multiple overlapping candidate keys, and it offered to give the standard example that only if pushed. We have anomalies and why we normalize. Why do we need the normal forms? So the perfect answer is that we need normal forms is that we need to reduce redundancies plus 3 anomalies with an example. So the perfect why anomalies answer is that a table is in 3NF stores redundant data. So a table that is not in third normal form, it stores redundant data, and redundancy causes 3 anomalies. Because of redundancy, there are 3 anomalies like update anomaly, insert anomaly, and delete anomaly. So update anomaly is the fact that the same fact stores many rows, change it in one place, and the copies now disagree in consistency. So if you update it in one place, the copies of that data don't agree anymore because it's not in the third normal form. Then we have insert anomaly. You cannot insert one fact without intervening another. For example, can't add genre before any books uses it. So if genre lived only inside book, like if genre only lived inside the book situation, then you cannot add new genre if there is no book there. So you have to separate these two things because they are different. And then we have delete anomaly, where deleting a row destroys unrelated information. For example, delete the last book of a genre and the genre itself vanishes because you made it dependent the wrong way. You have to make sure it's 3NF. So normalization removes the redundancy and anomalies that we talked about, and by splitting into well-keyed tables, so each fact lives in exactly one place. Then we can have a concrete analogy from a library design where we imagine a genre stored as a text column on book, update renames as science fiction, and you can edit every science fiction book row, but if you miss one inconsistent, for example, delete remove the only specific book, and this basically disappears entirely. That's exactly why you factored genre plus genre book genre out. So what we don't overclaim is that normalization reduces redundancy but costs joins. It makes us, which is performance, of course. Sometimes you denormalize on purpose. You try to denormalize things because for a reason, which is precisely why the fine amount decision was created. So saying this shows maturity rather than dogma. Okay. Then our deliberate third normal form violation, the star answer. So our report kept fine amount in borrows even though it's derivable from due date and return date. That's a stored derived value. So a controlled denormalization presents it as a concise trade-off. That's not a mistake, but that's a concise trade-off. It's a decision that we took because the due date and return date, that's stored as a derived value. The two reasons is that audacity first. Fine amount plus paid are financial records. Storing the values freezes the fine as actually charged. Even if the daily rate changes later, for example, this happened in the SQL query, right? It can be changed, or a librarian manually adjusts it. So you can manually waive it for some people. If I want to waive it for someone, there's something called a hardship appeal, psychological burden. I don't know. There's something psychological burden, or there's a hardship case. Someone emails about it, and then I might just make it 0, and then they're waived for their fees. They don't have to pay for it anymore. So a purely computed value would silently rewrite history. Then the second thing is performance. There are two reasons for that. Then we have borrows as joined and queried constantly list unpaid fines. Overdue borrows reading a stored number is cheaper than recomputing date difference multiplied by rate on every report as the table grows. So this is performance. We know that this gives us a lot of control. And then we say that, okay, the level up answer for depth point is that strictly the functional dependency due date, return date goes to fine amount only holds if the rate is fixed and fines are never adjusted. But you argue fines can be waived adjusted, which means that the same dates can map to different fine amounts. So if so, the functional dependency doesn't actually hold, and it's not truly a third normal form violation at all. It's a legitimate independent fact. For example, a snapshot offer both reading. It shows you understand what a functional dependency really requires us to do. Then we have how would you fix it if you wanted strict third normal form. So we draw fine amount, we compute it in a view or a generated computed column from due date, return date, and a fine rate table. For example, rate keyed by date, so historical rates are preserved. That keeps audibility without storing a derived value. The by the book solution, naming this alternatively, is exactly the reflection they reward. Then we have report also mentions a trigger, what for and why not a constraint. To stop the same physical copy being lent to two unique students at once, we check for an existing active loan return date is null. Before inserting a plain unique constraint can't express unique only among active rows because a copy is legitimately borrowed many times. MySQL actually lacks partial filtered unique indexes. So PostgreSQL has them. So a trigger enforces the rule instead. We have great multi-user integrity, taking point goes to bridge into section. We have that in section 10. Then we have two tiny tables, S which is student, B is which is borrow rows by student ID. So we take note S has Tom and ID 3, no borrow, and B has borrow for ID 4, so no such student. These expose the joint differences. Then we can see, okay, we have inner joint, we have the condition SID B SID, where we say, okay, SID here and we say B SID here are equal. For example, inner join is something that might say, okay, the result is rows. So what we get is that max, we get this, we get HP, we get max 1984, we get Anna shining, Tom and ID4 dropped. So this is dropped and this is dropped. So Harry Potter we didn't got again. We have a left join, S left S dot SID equals B dot SID. So the three inner rows and like the three inner rows, these three rows, and the Tom is null because it doesn't have a match to it. So we are doing suppositive match based on these IDs, and because there is no connection here, so this becomes null, but this still is displayed because we keep both sides full outer join. We keep both the sides. Here we keep one side, here we keep both sides. In an inner join, the SID only appears once. In cross join, there's a Cartesian, we don't have a condition. In semi join, we only have max Anna 5 column only, no dupes. And in anti join, 5 rows and no match. And theta join is join inequity. So what is the impact of inner versus left? Inner keeps only matched pairs, used when you only care about students who borrowed. So inner keeps matched pairs. For example, you might see this inner join here, that it only kept the matched ones. For example, it says the Harry Potter, so one matched the one, so we had these both because they matched. Max and 1940 because they also match. These match. Anna Shining, this and this also match, but Tom, this and this are dropped because they don't match. So whatever is this here and this here the same, they come out. That's the inner join. The left join is that 3 rows plus Tom null. So what's not in left join, what's null is also written. So we understand left keeps every student including non-borrower, use for list all student and their loan amount, the impact rather unmatched left row still with nulls. So even if the left row is null here in inner join, we didn't wrote what was not matched, but on the left side, even if on the left side something doesn't match the right side, we still write it and we say 0 there. So Tom null. So the 3 sides come and nothing else comes. Like these 3 comes which matched basically, plus the Tom with null. And with the right join, it's the same thing, but here we keep this and we remove this, and we don't write this, we write this with a null. This is the right join. Full join is that we keep both sides and we give the null because they didn't match it, but we still write it. Natural join is inner join, but SID appear once. So it is inner join, but the inner join plus the ID appear once. So it comes 3 and then comes 4. So 1, 2, 3, 4 like this, and whatever matches comes only once. That's natural join. Auto match, same named columns, SID appear once. Cross join is not a condition, it's just 3 by 4, 12 rows, it's a Cartesian product. Semi join is S row where S rows where exist match. For example, match and a S column only. For example, it's a condition where you have a condition that do this only in this situation. Anti join is the S row with no match. So if there is no match, for example, Tom, SID S rows with no match, it's Tom, only Tom, and theta is any predicate, for example, where SID is less than BSID. Join on non-equity condition. You have semi-join without writing all its columns. So a semi-join returns rows of the left table that has at least one match on the right, only left column, no duplication. In SQL, where SID in select SID from B or where exist. As our professor said, use abstract tables. You answer with existence, not writing a huge product. Then we know that there's a natural join where why can it be dangerous? It auto joins on all identity name columns. If 2 tables share an incidental column name, example name, it silently adds an unwanted equality and returns wrong empty results. So we prefer explicit join on in real code. Then we have transactions, scheduling, and asset properties. So asset is one crispy line, and library example, atomicity, all or nothing. These are asset principle. Atomicity first. Atomicity is like all or nothing, a loan that decrements availability and inserts a borrow row, either fully commits or fully rolls back. So consistency is a transaction moves the DB from one valid state to another. All constraints, foreign keys hold before and after. So we have consistency in the schema. You have transaction moves from DB from one valid state to another. all constraints fell foreign key hold before and after. So it's not that okay, this was foreign key today, tomorrow there's something different. This is the primary key today, tomorrow there's something different. Every day these things change. It doesn't work like that. You one time you define, okay, this is going to be the primary key in my project, and that's going to be like. Then we have isolation. The concurrent transactions don't see each other's uncommitted work. The result equals some serial order. So we have serialization. We have isolation, which means serialization there. We have concurrent transactions that don't see uncommitted work of each other. And then we have durability. Once we commit it, it survives crashes. So written to disk log, for example. That's how it's durable. Then we have concurrency anomalies. What isolation prevents is it prevents dirty read, reading another text sends uncommitted change that may be rolled back. So he rolled back, and that's a dirty read. He didn't even do it, he rolled it back, but because it's uncommitted, now you read what he rolled back. Now non-repeatable read. Rereading the same row gives a different value. Another transaction updated it in between. So if somebody in between updated the transaction, it's non-repeatable read because you're rereading the same row. Gives a different. Right now you read it after 5 minutes, it's different. There's a phantom read. Rerunning the same range query returns new rows. Another transaction inserted matching rows. So you rerun same range query, for example this range to this range, it returns new rows, so new rows are added now. Another transaction inserted matching rows, so they added new rows to it. We have lost update, where two transactions read or modify write the same value, one overwrite is lost. So one person who overwrote it is gone because both of them are overwriting the same thing. So isolation level is read uncommitted, dirty is possible. So if it's dirty read, isolation level is possible. Then non-repeatable read is still possible, phantom read possible. Read uncommitted, dirty read is prevented. Non-repeatable read is still possible, phantom read is still possible. Readable read is prevented, dirty read is prevented, non-repeatable read is prevented, phantom read is still possible. But with serializable, dirty read is prevented, non-repeatable read is prevented, and phantom read is prevented. Then we have another technique called scheduling and serializability. A schedule, this is the same thing that prevents all of these three anomalies. These are actually anomalies with concurrencies. Then we have a scheduler, part of the database management systems. It interleaves operation of concurrent transactions. A schedule is serializable if its effect equals some serial, one after another execution, the correctness goal. So we have 2PL, two-phase locking. It guarantees serializability, a growing phase, acquiring locks only, then a shrinking phase, release only. So this is two-phase locking, growth and shrinking. Strict 2PL holds all locks until commit, also prevents cascading aborts. So wherein our project is a transaction concurrency issue. So the borrow operation, check the copy is free, no active loan, insert the borrow row under concurrency. Two librarians could both pass the check and double lend, a classic race. So our trigger is that return date is null check plus proper locking, a transaction closes it. This is the answer they're fishing for. So we know that. How do we know a schedule is serializable? We draw a precedence conflict graph. It's called precedence conflict graph, a node per transaction and edge. So Ti transaction reads A goes to Tj. When Ti has conflicting operation, read, write on the same item before Tj, no cycle for example, that is conflict serializable. So if there is no cycle, you can do conflict serializability. Offer to sketch it if you if they give you a schedule. So a node per transaction and edge. When Ti has a conflict operating read and write on the same item. So no cycle means conflict serializable. Database architecture and data abstraction. We have anti Spark 3-level schema architecture, which is data abstraction. We have external view level, what each user app sees, librarian active loans view, many external schemas. Conceptual, logical, the whole database logical structure, tables, column, keys, constraint, one schema. Then we have internal physical level, how data is actually stored, the file, the indexes, things on the disk. And what matters is that independence, logical data independence. Change the conceptual schema without breaking views. Physical data independence is change storage index without touching the logical schema. Apps stay stable while intervals evolve. Then we have DB versus database management system versus database system. Database is the organized connection of data itself. Then we have database management system, the software managing it, query processing, then we have transactions, scheduler, storage, security, and MySQL, etc. And we have database system, the whole package, database plus the database management system plus the applications plus the users. And then we have why several data models, for example, design pipelines, conceptual model, ER diagram, real world things and relationships, tool independent, and we have logical model, relational schema, tables, keys independent of any specific product, a physical model, actual SQL types, indexes, engine choices for a specific database management system. Then we separate them so the design survives a change of technology, which professor noted is why they test SQL theory, not just fragile tech specifications. So the admin lecture covered why a web app, a server, SQLite, what to say. So we frame it as application has 3-tier architecture, presentation architecture. So they say that why a web-based, a server, SQLite. We have a 3-tier architecture. Application, for example, browser, mobile UI. Application logical tier is PHP server. Data tier is the database MySQL or SQLite. Separation lets each tier scale and change independently. We distinguish this app 3-layer from the ANSI Spark 3-level schema above the same word tier. We have different concept naming the distinct score points. Then we know that SQL sub-languages, and we have some injections. For example, that SQL is not just a query language. We need to know 4 sub-languages and most common DB attack plus its fixes. We have DDL, data definition. Its purpose is to data alter structure. It creates, alter, drop, truncate. We have data manipulation, read, change data, select, insert, update, delete. This is what we do with data manipulation. We have data control, DCL, permissions, grant, revoke, transaction control, transaction boundaries, commit, rollback, and save point. And we have SQL injection, the most executed database attack. What user input is concatenated straight into a query. So input like or 1 equal 1 changes the query's logic by passing authentication, dumping, or destroying data. We have the most executed database attack, which is called SQL injection. The prevention is that parameterized query, prepared statements maybe. Data is bound separately from SQL text, so it can be never parsed as code. We have defense in depth, input validation, for example, escaping least privileged database accounts, stored procedures, ORM, and WAFS, but prepared statements are the core fix, for example. Then we have select all from students where email equals to plus input plus. So we fixed it by saying select all from student where email equals to this. With the value bounded as a parameter, the database treat is as a purely data. That one sentence is the answer, for example. So instead of saying, okay, in here we are able to say select all from student where email equals to and input equals to this. For example, we give email this plus input plus this. And this is inherently wrong. What we can do is we can say select all from students where emails equals to this, and if he puts it the wrong email, we can always indicate that this doesn't match to the right email address. This has nothing to do with, but then we can use forms of checking if this is even a valid email. Then we have generalization and specialization. Our project doesn't use it, but we have slides, and there is possible. So specialization is a split a general entity into sub-entities with extra attributes top down, a general member, student member, staff member, for example. Then we have generalization, the reverse merging common attributes of several entities into a parent bottom down. The parent holds shared attributes, for example, children add their own and inherit the parent key. Drawn with an ISA triangle in Chen notation. That's generalization. We have constraints, we have disjoints versus overlapping. Can an instance be in two classes? And total versus partial. Must every parent be in a subclass? Things like these are constraints. And we have mapping ISA to tables, three options. Single table, one table with all sub-attributes, a type column, null for the non-applicable ones, table per subclass per parent. Parent table plus one child table, each sharing the key. So this is a join to resemble. And we have table per subclass only. So one table per child with all attributes duplicated for disjoint plus total. So where could your library use generalization? A person, super entity, generalizing student, and author both have name, birth, info, or a library item. For example, parents specialized into book, DVD, or journal. You must not to because your scope only needed students and books, and ISA would add joint complexity for no current benefit. Then we have a clean reference. Then we need to be prepared for these report traps because we read into inconsistencies in our documents. If the examiner spots them, we need to be prepared and name them. So genre, it's a typo in the schema. Lists table as genre ID, a typo for genre. So we created table correctly that says genre. If asked to say typo schema and the actual table is genre as DDS, we don't have a problem. So book inserted has author ID and genre ID columns that don't exist in book. So we exist these values add author ID and genre ID, but book's schema has no such columns. For example, this is a direct contradiction. An example would bounce your answer. The many design means author genre belong in the bridge tables, not on book. That inserts in leftover from an earlier single author draft. The correct load inserts into book author and book genre. Then state the fixed pure reflection. Then we have author birthplace versus birth country mismatch. We have defines birthplace varchar, but the insert uses column. For example, birth country with values like England, USA. We pick just one birthplace and note that the sample data is country level. Then we have copy table lists as ISBN as int. This is again like just a data insertion, but ISBN contains hyphens and we currently use the right data type, not a number. It's just good that choosing SQL data types. The author borrowed most queries groups by book, not author. So this is something different. So we have rapid fire questions. We have to drill this out loud. Exams together by paying investigator. So walk me through your ER model in 60 seconds. We say 5 entities: student, book, author, genre, and weak entity copy, composite key, book ID plus copy ID, many to many. We have book author and book genre, book one to many copy. We have foreign key on copy, student many to many. We have copy resolved by borrows, which carries the loan attributes, dates, fine, paid, etc. Why is borrows a relationship with attributes and not just an entity? It records a borrowing event linking a student to a specific physical copy. Its attributes: borrow date, due date, return date, fine paid, describe the event, not either participant, for example. Then we model as a relationship. It maps to a bridge table. Then we have take book genre translated to tables, for example. Then we have many bridge books genre. We have book ID, genre ID. We have PK, primary key, both columns each, and foreign key to book and genre respectively. So we have book genre is many to many bridge. Then we have a book genre, where we take both of these as keys here, and primary keys both columns each, and foreign key to book and genre. So what does group by do, and what must appear in select? Collapse rows into groups per grouping columns. Every non-aggregated select column must be in group by or functionally dependent on it. Aggregates, counts, or sums run per group, for example. Difference between where and having. Where filters rows before grouping. Having filters groups after aggregation and can reference aggregates. What's a candidate key versus primary key? Candidate is a minimal super key. Any could serve, so primary equals to the chosen one. There can be several candidates but one primary key. Is our schema in third normal form? Yes, except a deliberate exception. Fine amount is a stored derived value for audit plus performance. A conscious denormalization, we can see name the 3 anomalies, update, insert, and delete. They're all caused by redundancy that normalization reduces. We have state, acid, we have atomicity, consistency, isolation, durability, and with the loan example ready, we have what prevents a copy being lent twice at once. A trigger checking for an existing active loan return date is null. A plain unique can't target only active rows, and MySQL has no partial unique index. Then what is a view, and is it stored? A name stored query acting as a virtual table, for example active loans. A normal MySQL view isn't materialized, it's expanded at query time only. It's a special feature of MySQL. So we have most common database attack, and it's fixed. We have SQL injection, we have fixed parameterized or pre-prepared statements, and we have bind data separately from SQL. We cannot say that the data has to be contained in the SQL. We bind it separately, and then we say that we create parameterized prepared statements that it cannot be longer than this, or this cannot be has to be following a certain standard. Then we have difference between database management system, and database system. Data itself, the management software, this is the managing software, and the whole package, data plus database management system plus apps and users. Which part of database management system orders concurrent operations? We have the scheduler. The goal is a serializable schedule typically enforced via strict 2PL. We have left join versus inner join on books and borrows. The impact is that inner drops never borrowed books, and left keeps them with count 0. So the inner basically drops the never borrowed ones, and the left keeps the left side with the count 0. Choose by whether 0 borrow books matter. Why is surrogate key instead of name titles? Name titles aren't guaranteed unique or stable. Surrogate keys are stable, compact, simple foreign keys. Then we have what makes copy a weak entity. Existent dependency on book and no standalone key. Primary key borrows the owner, for example. We have book plus copy ID. Physical versus logical data independence. So we have change of storage indexes without touching the logical schema, for example, that is physical. We have changed the logical schema without breaking user views. This is logical. Then we have final reminder. Start every answer from what you actually built, then go outward to the theory, then begin from your project on purpose. Talk only what grade what you say. Silence equals to 0, even if you know it. When you understand something, do it. Draw the table, join the graph rather than describe it. That's the whole difference. If they ask something, I will draw it. One small mistake in an otherwise confident correct answer is fine. Confidence and reflection carry you. So this is the whole concept.